Let's take a look at this shiny app for the binomial distribution for a couple of minutes. This one defaults to 6 trials for n and the probability of success of 0.5. So you can imagine flipping 6 coins and counting the number of tails or the number of heads. It provides a nice graph that looks almost like a histogram there with our different outcomes and their probabilities of success. It looks symmetric in this case, it is. It looks like our highest number of successes would be 3. The probability of seeing that would be about 31.25%. So notice even if you flip 6 coins, most of the time you're not going to see exactly 3 heads and 3 tails, but overall you see those higher bars near the middle of 3 there. We're expecting to see close to 3 tails or heads, but it could go either way a little bit. That's kind of exaggerated more as we actually let's do the number of trials up to say 80 maybe. As we flip many coins instead of just 6, we can see that even if you go all the way up to 100, you'll see that too, right? You can see that the probability of each individual outcome is very small, right? Notice it's actually constructing this probability table down here for you too. Most of those probabilities are 0 when we round to 4 places. This means that those events are very unlikely to happen. We're expecting to see outcomes near the mean, near 50. We're expecting to see roughly 50 heads and 50 tails if we flip 100 coins. But again, that exact outcome is still only going to happen about 8% of the time. With higher n values like this, you can kind of see that it makes more sense to think about ranges instead of individual outcomes. We might think in the range of 46 tails up to say 54 tails. If we add those probabilities like we can do in Excel pretty easily, we may see a more meaningful interpretation of probability there. A lot of times we're expecting to see outcomes close to the mean there. You can also click this checkbox to enter your own numbers in for n and p, and you can click this box to overlay a normal distribution. Notice that we see that this is still roughly symmetric, and actually this one's exactly symmetric, but we can also see that it's approximately bell-shaped there. Notice what happens though as we kind of shift that probability of success. One of the problems we'll look at is talking about airline flights. I think there was a 78% chance of them being on time. Notice what happens to our curve as we slide that over. Looks like it's shifted to the right end of the graph. Looks like the mean is kind of on the right end. This one still looks kind of symmetric there, but if we decrease the number of trials back down, think about what happens. We're decreasing that down to say 20, or now down to say maybe 10. If we go back down to even 10 flights at a chance of being on time of 78%, notice that it's definitely got a little bit of skew there. We can see that even without that distribution there, right? We can see that these bars are kind of piled up higher on the right end, and there's a tail forming to the left side. So we would say that this looks like a left skewed distribution. We're expecting a large number of on-time flights, if that's our context, whereas those outcomes 0, 1, 2, those have very low probabilities. Even 3, 4, 5 are a much smaller chance of happening. So that's what's causing that left skew in this case. You can imagine if we think of a different scenario with a small probability of success, like say 10%, you can see the opposite situation happening. Our data is kind of clumped in the left end, where our probabilities are highest for low numbers of successes, and that's creating, in this case, a right skew, where we're not expecting to see those outcomes in the upper end very much.